Welcome back, everybody. So today we're going to be talking about a new topic, specifically quantum error correction. And the basic idea of quantum error correction is that unlike everything else, where we're trying to in some ways, squeeze as much efficiency out of a quantum computer, now what we want to be able to do is introduce redundancy into the quantum computer to give us the ability to be able to detect and ultimately correct errors inside a quantum computation. So let me begin by sharing my screen. And now going over to OneNote. Great. So basic idea at a high level visually of what we're doing inside a quantum error correcting code is as follows. Imagine this is the Hilbert space or the vector space that ends up describing our entire quantum system. So this is a whole quantum computer. So this is the entire vector space on the quantum computer. So if this is like n qubits, then this vector space is in C2 to the n. Okay, normally what we would do is we would have our quantum states being literally anything inside this space. The idea, just visually about it, is instead of making the whole space valid quantum states, we're going to choose a subspace of this larger quantum system. This subspace that we're going to be doing all of our computation in is what we're going to call the code space. Okay, and so every state that is in the code space, we're going to treat as valid. So valid states are in here, and invalid states are here. And the basic idea behind quantum error correction is that what we would like to be able to do is we'd like to be able to divide our space up in such a way so that we can detect whether a state is in the invalid space and come up with an algorithm for mapping that invalid state back to the nearest valid state. And if this quantum error correcting code is chosen well with respect to the actual errors that we have in the system, then the probability, a good code, the probability of mapping a code word, which is a state in the valid space, with an error back to the valid code word is high. Okay, so that is essentially the idea. And the entire art of this, at least, from our perspective, is really just going to be able to come up, is going to be the art of coming up with good ways of projecting ourselves into the code space and detecting what the nearest code word is to a particular quantum state. So to understand how we could go about doing this in a less abstract way, let's jump back to ordinary computing and take a look at the repetition code. So the repetition code is an error correcting code that I'm sure you all know. And the basic idea behind this is that what we do is we just repeat bits in order to be able to encode information. So instead, normally imagine we've got two parties, right? We've got Alice on this side and we've got Bob on this side. And Alice would like to send a bit string to Bob. Let's say it's 0, 1, 0, 1. Yes, I know I'm so bad at generating random numbers, but in any case, say Alice wanted to send these across, but the problem is that, in between, you've got a noisy channel that sometimes is going to end up destroying or corrupting pieces of information. And so the question is, well, how can you deal with this? Well, it turns out in general course, you can't necessarily deal with this. If the environment has the ability to choose noise completely adversarially, then they can always do it in such a way as to ruin Alice and Bob's day. But if we make some assumptions about the noise, then actually that ain't true anymore at all. And so the simplest noise model to consider for this case is, let's assume that each bit sent is flipped with probability p across, and assume that this is an IID process, or independent and identically distributed process for each of the individual bits that are coming through. So given this particular case, a natural strategy for Alice and Bob to settle on before coming in is to say, well, let's take our logical bits that we want to send across and encode them redundantly. So here's a simple way that we can redundantly end up encoding as 3 zeros or 3 ones. Now, in the event that this noise ends up happening to one of Alice's code words, then in that case, what will end up happening is Alice, instead of say sending 000, she'll send 001. And this will happen with probability p times 1 minus p squared. Because here we'd have to have an X error, and here we'd have to have a not X error. Is it not a bit flip on both of those locations? So the basic idea is that Bob receives this. Now Bob, again, knows that they're making this assumption about the noise in the system. So Bob has two choices. Bob could either say, case 1, Alice sent 000. Case 2, Alice sent 111. Both could conceivably do this. However, the probability of case 1, given that 001, oh, sorry, actually, I did draw that right. Case 1, given 001, is actually just equal to that likelihood I wrote at the top. It's p times 1 minus p squared, because 1 bit would need it to be flipped in order to make this happen. However, the probability of case 2, given 001, is equal to, well, in this case, 2 bit flips have to happen and 1 not bit flip. So this probability is going to be p squared, 1 minus p. If p is less than 1/2, which we need in order to ensure that the channel even makes any sense, we need to, the probability of case 1, given this data, is higher than case 2. So Bob will use the maximum likelihood estimator, or MLE, to guess that Alice meant to send 000. And so what this ends up meaning is that the probability of an error that that we end up getting is that goes from prob error equals p to prob error equals p squared 1 minus p, which is just equal to p squared plus order p cubed. So this essentially quadratically reduces the probability of Bob observing an error. And in general, we can make this error switch go down exponentially. And so the easiest way of seeing this is like, okay, well, let's now, if we want even lower probability, we could end up using a 5-bit code. This is equivalent to 0 and 11111 is equivalent to 1. Okay, So then in this case, in order for Bob's maximum likelihood decoder to make a mistake, 3 errors must occur in order to create that. And the probability of that is, again, equal to p cubed 1 minus p squared. So in general, a 2n plus 1 bit repetition code can reduce the probability of error from p to what? It'll be to to order p to the n plus 1. Okay, so this implies that we have an exponential suppression of error at a polynomial space overhead. So going back to, kind of our view of the, let's now instead consider Alice sending probabilistic bits across. So now Alice is going to send to Bob a probability distribution. This probability distribution will be P of 0 equals, let's call it A, and P of 1 equals 1 minus A, for just sending a single probabilistic bit to Bob. So Alice sends a probabilistic bit to Bob. And so if we envision in this particular case, the valid probability distributions that Alice would have would be of the form, the encoded distribution would be A 0, 0, 0, or sorry, the encoded distribution would be 0, 0, 0 with probability A, or 1, 1, 1 with probability B. Using the notation that we used for probabilistic reversible computing at the beginning, this probability distribution could always be written as, 1 minus A. We would call this A E 0, 0, 0 plus 1 minus A E 1, 1, 1. And then all valid probability distributions would sit inside this vector space in this code space. So for example, we might have some particular probability distribution, which would be 1/2 E 0, 0, 0 plus E 1, 1, 1. However, if we ended up getting the case 1/2 E 0, 0, 1 plus E 1, 1, 0 out here, then we would like to be able to, by just taking a look and applying this error correction strategy, we can see that the most likely distribution that we would end up getting for this would be this state over here. And so this is how we can think about generalizing this idea over to the case of quantum. Because now, instead of having a probabilistic distribution of this, we now have a quantum distribution. Now, there's one big difference that ends up happening here. With a probability distribution, you could envision that a third party could measure and correct the individual bits coming through without changing the apparent distribution that Bob would end up reading on the other side. However, quantum doesn't obey that. Any attempt by one of the parties to measure in order to correct the errors will screw it up. So another way of putting this is, because measurement is active in quantum, we can't simply measure to apply error correction. And this actually, historically, was kind of led to an interesting period in quantum computing, because in the early days of quantum computing, there was a lot of excitement about the possibilities that quantum computers could potentially have for speeding things up. But the biggest problem was that many people didn't believe that actually a quantum computer could be error corrected. And because of this, and simply this inability to error correct them was assumed to be just because of the fact that any attempt that you end up having to take a look at, a quantum code, like let's imagine we had a quantum version of a repetition code. We might, try to look at a state that would be A00 plus B111. Any attempt to look at this would end up killing our state and then just yielding 000 potentially back out of it if we measured it. So because the act of measurement ends up having this action, folks thought that actually it's going to be impossible to build a quantum error correcting code. But fortunately, that wasn't exactly true. Quantum error correction indeed is possible, but it's just we have to be more sensitive and think more clearly about how we end up performing our operations on it. And so the key idea behind error correction, behind making error correction work, is applying projectors. So let's take a look at the simplest possible case. So in this lecture, we're going to just look at a quantum Bitflip code first. And then we're going to generalize that later to the phase flip code and show how to correct against arbitrary errors to begin with. So let's assume that what we have is we have the following type of error. Let's say that we have our space set up like this, and we have our quantum state down here, which will encode in a 3-qubit repetition code for simplicity. Let's say it's A00 plus B111. Okay, and now let's assume that what we do is we are going to mess with it. And the way we'll mess with this particular quantum state is that we'll imagine we've got some other state out here, okay? And I'll call this state this is the valid space, AKA the code space. And the remaining space is the space of errors. And I'll call this state psi perp up here, okay? Let's imagine that our valid state ends up getting mixed in due to some quantum process with a state from the orthogonal complement. So we're going to model our error for this first example as error. This error channel ends up mapping A000 plus B111 to cosine theta A000 plus B111 plus sine theta psi perp. Okay, because psi perp is in an orthogonal subspace to the code space, we know that this is a normalized vector. So this is a valid vector. So how could we perform error correction? Well, the basic idea is that what we would like to do is we'd like to just simply remove the sci-perp component of the vector. If we do that, then we're actually just left with our original vector that we ideally wanted to store. So how do we remove this sci-perp component? Well, the easiest way is to apply the a projector onto the code space. So in our case, what is the code space? Well, the code space is just simply the span of the two valid logical code words in this. And the valid logical code words are are 0 logical equals 0, 0, 0, and 1 logical equals 1, 1, 1. So the code space is then the span of 0 logical, 1 logical. Just like our ordinary single qubit space would be the span of 0 and 1. But if we look at this in our entire space, this of course is just the span of 0, 0, 0, and 1, 1, 1. And of course, looking at it from the perspective of the physical bits that comprise our logical bits up here, this subspace actually doesn't encode everything, just as we end up seeing in this diagram here. Okay, so we have every vector inside the code space is spanned by those. So the projector onto the code space can actually just be written as 1, 0, 0, 0, or projector onto 0 plus the projector onto 1. And we can end up seeing that this projector has the property that any state of the form A00 plus B111 is equal to, well, this projector acting on this will just yield 1 times that vector. This acting on this will yield 1, but the cross terms are going to yield 0. So this is just A000 plus B111. So it ends up keeping this state intact. However, PC acting on sci-perp has to be equal to 0 because sci-perp is orthogonal to both 0, 0, 0 and 1, 1, 1. So there you have it, okay? But if we could figure out a way of applying this non-unitary operation to our slightly erroneous quantum state, then we could trim off this portion of the quantum state that we don't want and just keep the part that we do want. So how could this work? Well, fortunately, we actually have good methods for applying projectors like this. We can use linear combinations of unitaries. To build PC, or more broadly, any projector. So the strategy for this goes as follows, right? Very first thing that we want to do is we want to consider constructing PC in terms of unitary operations. The easiest way of doing this is, one, translate projector into a reflection. Okay, and the way that we can do this is we can end up, say, for example, we let RC equal identity minus 2 PC over here. And RC will have the property that RC acting on sci-perp equals sci-perp, but RC acting on something inside the code space, such as A00 plus B111, will be equal to minus A000 plus B111. And you could just go through the definition of the projector in order to verify that this reflection actually has that property. So that's the first thing that we need to do. We need to write it as a reflection operator. Then we can end up saying, well, once we've written it as a reflection operator, we can write PC then, which is the projector that we want to actually implement, as just being identity minus RC divided by 2. Then 3, we need to find a way to build RC. And then 4, use LCU in the following way. The simplest circuit for implementing this would be H over here, RC, H measured. Okay, so this actually is also just the Hadamard test circuit, but I'm expressing it this way in terms of projectors because of the fact that it's easier to think about its action on the space, at least, from the perspective of the ordinary language that we use in quantum computing, by taking an active rather than a passive perspective on it. So when we end up doing this, we can end up seeing that if this state was psi down here, then 0 psi from the LCU lemma just ends up getting mapped to identity. Actually, I guess technically the easiest way to express this is minus RC. So we want to be able to figure out a way of building minus RC, but okay, let's not worry about that. So minus RC will go to minus RC over 2, 0. Oh, sorry, I guess actually I don't need the half here because it's already in the other term. 0 psi plus 1 identity plus RC divided by 2 acting on psi. Okay, cool. So then basically, if we measure this first qubit, then we'll get the correct response, as in we'll get psi mapped to the projection of psi divided by the length of the projection acting on psi, coming back out. Okay, yeah, let me use matrix. Yeah, cool. So this is what we'll have, which corresponds to exactly what we wanted to do to begin with. We wanted to be able to apply the projector on our erroneous quantum state and project that back out. And in our case, the probability of doing this for our example would just be psi identity minus RC over 2 squared psi, which is, because this is a projector, it squares to itself. And so this is just identity minus RC divided by 2 acting on psi. Okay, so this is what we end up having. And for our example, this is just equal to cosine squared theta. So what this means is with probability cosine squared theta, the psi perp component is removed. However, with probability sine squared theta, the code space part dies. And so that in general could be a pretty bad thing. If we were just using this tactic alone to try to suppress errors, this would work, and this would actually lead to a quadratic suppression of errors. And in some cases, if we did this frequently enough, we actually could end up, in principle, sucking all the errors out of our given state, assuming a whole bunch of things. But the problem is that a single failure takes us outside of the code space. And then the question is, well, how do we return? Well, in order to return, so this is, how do we return to code space? Well, in order for this to happen, we need to actually be able to do something very similar like the repetition code. With the repetition code, what we had that our individual states, we were capable of correcting them because of the fact that we had a model that we had in our heads for how errors ended up occurring. And that allowed us to find the most likely vector in the code space that would have led to the particular vector that we see outside of it. But again, how do we do that without actually screwing ourselves over in a horrible way to do this? Well, the basic idea visually behind all of this is to, one, assume a noise model. And a noise model that we're going to assume poly applied to with probability p. Okay, so that is the noise model that we're going to be taking in this particular case. So the next question is, well, how do we get enough information to work backwards? Well, the basic idea behind this is that what we can do is we can subdivide our space of errors. So the way we can subdivide our space of errors is as follows. Okay, let's consider that we had before, when we were just doing our PC error, we were just projecting onto two spaces. We had our projector onto the code space, which projects onto this as its range. And then we have the identity minus PC, which projects onto this. So in order for us to be able to figure out, what quadrant or what part of the space that we're in, what we're going to do is we're actually going to divide up our space over here into, instead of 2 regions, we're going to divide it up into 4 regions. And this will be enough information for us to actually be able to work backwards and determine whether an error happened on no qubit, in which case we got the code space, the first qubit, second, or third. And the way that we're going to do this is we're going to take a look at the structure of our code. The structure of our code words was as follows. We're going to have 000 and 111 as our 2 code words. You'll notice that there's a beautiful symmetry behind it. Both of these code words actually have even parity for the first 2 and even parity for the second 2. So the parity of first and second qubits is equal, and same and third, second and third is also. The information from the first and third is redundant. So what we can do is we can check these parities to further project R to one of these. So specifically, if we just were to apply the code projector our quantum state could be in some arbitrary superposition of errors happening in all the other places. What we're going to do is we're going to perform a series of projectors in such a way as to instead force our quantum state to only be in one of these sectors that has a discrete error acting on it. And here's how we can do it. The way we can do it is as follows. So we can write PC is equal to P12, P23. Now, P12 has the following property. So P12 acting on the following state, 1, 1, will be equal to 1, 1. And P12 acting on the state 0, 0 will equal 0, 0. But P12 acting on 0, 1 will just be 0. So essentially, P12 acting on a particular state. So P12 has +1 eigenvectors equal to even parity bits. And similarly, P23 has the same. So if we apply these two projectors, it's exactly the same information ultimately, or applying exactly the same projector ideally as PC, but the measurements that we carry out are actually going to give us more information and constrain the state more in an individual space. So specifically, let's see how this ends up working. So for P12, we have that P12 acting on 1, 1 is equal to, or sorry, we have that R12 has to, in our particular case, map 1, 1 to -1, 1 and 0, 0 to -0, 0. Or negative R12 has to map 1, 1 to 1, 1 and 0, 0 to 0, 0. And of course, I forgot to mention 0, 1 has to go to -1, 0. So that is how we can end up viewing the R12 operation. So now let's go through and ask, well, how can we build something that ends up looking like -R12? Well, R12 actually, -R12 is actually just this operation. It's just the controlled Z gate. And similarly, -R23 can be viewed as the following. If I express it as a 3-qubit circuit, it would be this. Z. Okay, cool. So then how could we end up building our non-deterministic code space projector using linear combinations of unitaries? Well, there's a couple of ways that I could draw the circuit, but perhaps the simplest way to draw it would be to begin with 2 ancillary qubits and apply a pair of Hadamards to it. Then we're going to have our actual state down here that we would like to be able to perform the projection on. And first thing, I'm going to apply, let's say R12. So the very first one is going to be R12. So I will apply, well, technically, I guess, -R12 to this. Oh, I'm sorry. No, this is wrong. Let me correct this. R12 isn't control Z, it's actually ZZ. And similarly, R23 is just ZZ. So this will yield us the following. Z, there we go. Okay. And now we'll do a Hadamard transform and another Hadamard transform, and then we will measure. And this will implement our projector. And the way that we can see this is actually, again, just by multiplication, because our P12, if we express this as a matrix, our P12 is of the form 0, 0, plus 1, 1, tensor identity on the third qubit, and P23 is equal to identity tensor 0, 0, plus 1, 1 on the remainder. So when we multiply these two things together, we just end up seeing that the cross terms between here and here are 0, and here are 0. The only two that end up actually multiplying are these. And so by multiplying those, we end up getting that this is 0, 0, 0 plus 1, 1, 1, 1, 1, 1, which is equal to PC. So we can see from the LCU lemma that this, if we end up measuring 0, 0, will actually correspond to the code space projector. However, in the event that we fail, what will happen? Well, instead of us applying P12 or P23, failure yields psi goes to identity minus, plus P12 over 2 psi, which is equal to the orthogonal complement of the projector, R12 here. This is the orthogonal complement of P12 acting on psi. So what this ends up meaning is that in the event that we fail, we're going to actually project onto the space that's orthogonal to the support of this. So for example, if we had a state that was of the form A00 plus B01 plus C10 plus D11, applying our projector and failing will end up mapping us to the orthogonal complement of the code space, or of the space we're trying to project onto. So this is in the domain of P12, and these two are in the domain of P12 bar. And so this will map us to B01 plus C10 instead of that. So that is how the action of our particular state ends up working. So what we can do is we can actually just take a look at the measurement results that we end up getting. So the measurement results corresponding to each of them basically can be thought of in the following way. We can view these actually as just giving us information about individual parities of the quantum bits. So this is the first measurement and the second measurement. And then over here, let's put our decoding. So if we have our first measurement and our second measurement being 0, then we have no error, as in we projected exactly onto the code space. Now let's take a look at the case where M1 is 1 and M2 is 0. In this case, what we've done is we've applied ourselves the projector P12 bar P23. And so what does this mean? This means P12 bar P23 implies that projector onto odd parity of qubits 1 and 2, and even for qubits 2 and 3 applied. And this projector, when we go through and actually do the multiplication like we did before, we'll end up seeing from this that this case of odd parity for the first two qubits and even parity for the rest of them corresponds to the following. We end up getting 1, 0, 0 plus 0, 1, 1, 0, 1, 1 as being our projector. So if we take a look at these two measurements, then, well, let's just take a look at this. This code space corresponds first qubit. Now, we need to come up with a way now for our decoder to map this back to a vector in the code space. So the way that we can do this is we can say, but our model assumed that is flipped with poor, the most likely error is x on, if this being wrong, is just as mentioned, squared p. Okay, so then the decoding that we end up getting from this is we end up getting that we have an error x identity, okay, which corresponds to P12 bar, P23. Now, if we end up getting, in the second case, a 0, 1, then what ends up happening here? Well, P12 is good. They're the same parity, but P23 is wrong. And so by multiplying through our projectors that we end up getting in this case, we end up finding that P23 times, P12 times P23 bar is actually going to be equal to, those two are good, those two are bad. So then this should be 0, 0, 1, 0, 0, 1 plus 1, 1, 1. So this will correspond to identity x. And similarly, this case down here, going through the exact same thing, will correspond to an error on both of them. And the only way we can get wrong, or the other two flip. And so the maximum likelihood decoder will say, oh, okay, well, the most likely solution is that the middle one is down. And so this gives us a way of decoding the error. And in the event that a X error happens discretely on a qubit, just go through the full analysis to kind of convince you that this is true. Let's say we begin with an arbitrary quantum state in the code space, A00 plus B111. And let's assume that we have a single error end up impacting it. Without loss of generality, error happens on first qubit. Then what we end up getting is we just get A100 plus B011. Cool. Now, if we try to apply our projectors to this, so if we apply PC is equal to if we apply this to our linear combination of unitary circuit, the application of P12, which is equal to, of course, 0, 0, 0, 0 tensor identity plus 1, 1, 1 with probability 1, because P12 acting on A100 plus B011 is just equal to 0. Therefore, we measure 1 in the LCU, which heralds a failure, P12 bar. to it, which in this case doesn't really do anything to the vector because the vector was already in the support of that projector. Okay, cool. So now we've projected away the first two. The next step is, step 2 is we apply, or we attempt to apply P23. Now this will measure 0 with probability 1. And the reason why is that P23 our state we get after the projection plus B011 plus B011. And the reason for that is of course because these two parities are both even, and therefore the projector is trivial acting on this. And so when we go through the linear combination of unitary circuit, the probability of us applying the orthogonal projector is 0 to it. So therefore, this will succeed with probability 1. So therefore, we have a state in the end, which is of the form A111, and we know P12 failed, 3 failed, or succeeded. This leads to the conclusion, likely a Bitflip error happened on the first qubit. Okay, and so then our decoding correctly maps, or sorry, after determining this, we then actually need to correct the error. So correcting error by applying X to first qubit, A100 plus B011 maps to 11, which of course is equal to just the state. So this ends up showing that against any single discrete error that we end up having in the system, we actually can correct that error without any difficulty, which I think is super cool. The other thing that actually I think is also pretty neat that we end up getting out of this is that we have the ability to actually be able to can also correct partial bit flips. So what do I mean by that? What I mean is, okay, let's assume that we have our code word, or our encoded quantum state, which is A00 plus B111. Then what I'm going to do is I'm going to apply e to the negative I x theta to qubit 0. And so tensor identity squared, and maybe not to qubit 0, but I'm just going to apply this state to it, this operation to it. So this will end up giving us cosine theta A000 plus B111 minus I sine theta A100 plus B011, using a fact that e to the negative I x theta is equal to cosine theta minus I sine theta x. Okay, good. So this is our particular quantum state. Now, what we'll do is putting state through our quantum error correction circuit, we find that unlike the previous case, this time there's going to be some non-zero probabilities for both of them happening, for projector 1, 2 firing. We find with probability equal to cosine squared theta, we obtain a 0, 0. We obtain the measurement outcomes M1 equals 0 and M2 equals 0. This corresponds to applying P12 and P23 is equal to the code space projector. And the action of the code space projector acting on our space is PC will just map us to A 0, 0 plus B 1, 1, 1. So this means no errors occurred. So another way of thinking about this is that our code space projector has actually actively removed all of the errors with probability cosine squared theta. Okay, now with probability equal to sine squared theta, we end up with the state A 1, 0, 0 plus B 0, 1, 1. Which this corresponds to applying P12 bar, P23. Now, there's no possibility of P23 bar because these states, even in their erroneous form, have even parity for the second two. So the probability of measuring those two states to be, those two bits to be the same is 100% because there's no possible quantum state in the superposition that doesn't have the same parity for those two bits. So we end up getting a probability of sine squared theta of this particular error happening. Now, as reasoned, this registers as an X error. Because what we end up seeing is okay, well, M1 equals 1 and M2 equals 0. And as established, if we go back to our kind of like decoding table that we had to work out all of this junk, we end up seeing that that corresponds to an X error in the first qubit, unsurprisingly, because it's just like what we talked about previously. And so applying X error to first qubit yields A 0, 0 plus B 1, 1, 1. And thus, actually, it's not just Bitflip errors. Thus, we can correct any e to the negative ix theta that we want. Okay, that's great. So we can actually do like a fractional X gate as well. So quantum error correction can deal with a fractional Bitflip. But it turns out that this strategy isn't going to actually be able to cover everything. One thing that it can't deal with is the Z error, but I'll get to that in just a second. I guess the first thing that I wanted to do is let's actually just lay out the entire quantum circuit for doing all of the corrections. So the entire quantum circuit, again, follows by doing our linear combination of unitaries approach in order to try to apply the code space projector. And we do it in those two steps in order for us to be able to disambiguate the possible errors that can come in. And we do it with a pair of Z gates going down here. Okay, and then what we need to do is we just need to go through and enumerate the different possible options. In the first case, if this one is 1 and this one is 0, then we, as mentioned, this corresponds to an X error in the first configuration. If this is 0 and the next one is 1, then from our lookup table, if you recall, that corresponded to an X error here because the parity of the first two qubits is correct, but the parity of the second two is wrong. And then the final one, of course, corresponds to the middle one being wrong. So let's just fill that in, where the double line describes the flow of classical information here. So this is just basically saying that those two measurement outcomes are 1 and 0, then apply an X error. And this is the complete 3-qubit Bitflip code circuit. All right, now the last thing that I want to discuss is I want to discuss the failure of Bitflip. Codes. Okay, and the main way in which they fail is, let's take a look at an encoded quantum state inside our code space, A00 plus B11, 1, I guess. Now, if we apply a poly Z on just the first qubit for this one, what do we end up getting? Well, this will correspond to A00 minus B111. This error maps something of the following. What it does is it takes this vector that we have over here, and it will map us to another vector inside the space that's of the form A0 logical minus B1 logical. So this acts just like a poly Z on this space. So this error is Z logical. And so an error from a single bit error that ends up happening on our encoded information is not protected against one iota. This physical error translates to an error in our interpretation of the quantum state, meaning that we don't suppress these errors whatsoever. So next time, what we're going to be doing is we're going to be talking about how we can actually change our Bitflip code to correct against a phase flip error, and then how we can combine those two to be able to not just detect and correct X and Z errors, but actually correct any error. So hope you enjoyed. See you all next time.